All right. And it's important to talk about the physics of blood flow, to think about how blood moves through the vascular system. So that is our first objective here. But let's first look at a poll question just to see how much we remember from AMP1. Few more seconds. Okay. So the order of the vasculature from the left side of the heart to the right. Most of you went with D, which is correct. It's arteries from the left ventricle, arterioles, capillaries, venules, veins, and then back through the right atrium to the right heart. Okay, so that is the correct flow of the heart. And if you recall this drawing, we talked about the left heart, left atrium being the receiving chamber from the pulmonary circulation, left ventricle being the ejection chamber towards the systemic circulation, starting with the large arteries, then branching, strategically to different parts of the body into arteries, arterioles, and then capillary beds. Capillary beds are the site of exchange. So very tiny vessels, the most abundant vessel though, and then venules converge to veins, which converge to the large elastic veins like the IVC, and those come back to the right atrium, then right ventricle. Right ventricle ejects towards the pulmonary arteries and then into the lungs. So that divides us into two general branches of the circulation, the systemic circulation, all of our peripheral tissues and organs, and then the pulmonary circulation going back to the lungs to drop off carbon dioxide and other waste gases and to pick up oxygen. Okay, so just to refresh ourselves of that flow, that's going to be important when we think about the different branches of the vascular system and the principles of blood flow. So our first objective here to apply the laws of physics in our understanding of blood flow and pressure. And again, understanding the laws of physics is going to tell us how blood flows, how it behaves as it moves through the vascular system. When is it moving more quickly? When is it slowing down, right? And what pressure gradients are needed in order to drive that flow continuously. So in order for us to identify how blood vessels will change and how flow will change, we want to think about these three general principles. The pressure gradients in the cardiovascular system. So we must have a difference in pressure for blood to move. Blood moves passively, okay, through the branches of the vasculature. And so high pressure coming from the heart, along with low pressure out in the vasculature bed, is what allows that flow. We'll talk about that pressure gradient, which drives flow. Another thing is resistance. So resistance is going to be encountered as we move through the smaller branches of the systemic circulation, the vascular bed. So this is going to actually be a force opposing flow, right? The more resistance we have, the decreased flow. And the decreased resistance is going to increase flow. So we can say the resistance is inversely proportional to our flow, right? And then thirdly, relating the pressure gradients to resistance. So again, that same relationship, pressure gradient is up when resistance is down and vice versa, right? Because the pressure gradient is the flow, it is inversely proportional to that resistance in the systemic circulation. So those three principles are going to be important to remember as we talk about factors that affect flow and the physical laws and principles of flow itself. So what are things that we know? Some things that we described in, cardio in AMP1. The circulatory system is closed, right? All the blood vessels are connected and blood never leaves the system. It's just circulating from one, bed, one system to the other. We can also use an analogy of water in a water hose to understand the physical laws that move blood. So we're going to bring that analogy up quite often. But the same way that the diameter of the hose, the flow rate of the water, the pressure gradient that moves the water through the hose, and other external factors like the water itself, the hose, and the diameter, all of those will affect how water is moving through that hose. Similarly, those principles will affect how blood moves through our vasculature. And so the pressure is going to be described as the force exerted by the blood. This is mainly the force as it leaves the ventricle and is moving throughout the vascular bed. Also, when you think about flow, it's from high pressure to low. So I mentioned this earlier, it's passive movement. So we need a gradient. If there were no gradient, there would be no flow. If the pressure in my heart was the same as the pressure in my radial artery, for example, blood would never move from the heart to the radial artery. So we need a gradient in order to drive that flow. And then I mentioned the resistance here. There are several other, factors that can influence resistance, but resistance itself is inversely proportional to the flow. It's a force that is opposing the direction of the flow, and it's going to slow down. So just to kind of summarize those concepts, the delta P is the pressure gradient, it's the change in pressure. So what this symbol here means, delta meaning the change, P meaning the pressure. And that in and of itself is the driving force that moves blood through our vascular bed, the same way that it moves water through a hose or any fluid or liquid for that matter through a conduit or tube, okay? The principles are the same. And then together, flow, we can call this bulk flow, the overall driving force or movement of blood is equal to the pressure gradient divided by any resistance that's encountered. So this is a law that, or an equation or rule that we want to remember and make note of in terms of the relationship between flow, pressure gradient, and resistance, okay? So let's look at some examples here. Now, flow, we said, is the owed to the pressure gradient, the change in pressure, and we can describe that as bulk flow, the overall movement of blood. The heart itself is what exerts the initial pressure on one end of the spectrum, which is what creates the higher pressure, followed by lower pressure, which creates the gradient. So the heart is really important in that pressure gradient. And then the heart is what sets up the movement of blood through the system by doing so. So if we look at the examples over here in scenario A, we have 100 millimeters of mercury on this side, left side, and then 60 millimeters of mercury on the right. So the gradient that we have is a differential of 40 millimeters of mercury. And that gives us a flow rate of about 20 milliliters per minute. So that's kind of the standard flow because we have a gradient. We have high pressure here, lower pressure here, and the difference is going to determine our flow. In scenario B, we have no gradient, right? The pressure on the left is the pressure on the right, and there is no change in the pressure. So the flow is 0 milliliters per minute, right? No gradient, no flow. And then alternatively, going back to scenario C, now we have higher pressure on the left side, lower pressure on the right. However, the difference is the same. So even though it's way higher in terms of the numbers, the overall pressure, the difference, the gradient ends up being the same. Therefore, the flow rate is going to be the exact same. And that is to say, if I were to increase the difference here, let's say we had 200 millimeters of mercury on the left side, but we dropped this down to about 100 millimeters of mercury, right? That would cause a bigger differential, a bigger gradient, and that would actually increase our flow. Okay. Now, thinking about how pressure gradients exist across both our systemic and pulmonary circuits, they're slightly different, but they wind up being the exact same. We'll talk about how. So the pressure gradient in the aorta, the pressure gradient across the systemic circulation is the pressure in the aorta minus the pressure in the vena cava. And we've talked about these values before in AMP1, right? We talked about the mean arterial pressure. This is the average pressure in one vessel, the aorta, throughout the entire cardiac cycle. So throughout systole and diastole, if we were to take the pressure in the aorta and we average that out across the entire cycle, that gives us our mean, our MAP, which is a very important number clinically in terms of the overall vascular flow. And then the other pressure is going to be our venous pressure. This is the pressure in the vena cava all the way at the end of our systemic circulation, and that is going to be our CVP, or our central venous pressure. So another way to look at the overall pressure gradient in the systemic circulation is to take our mean arterial pressure minus our central venous pressure. That will give us our gradient, and that will tell us the amount of, the rate of flow that is moving blood through the systemic circulation. So here we can see what that gradient looks like. Right here are our average pressures on the y-axis. And then we can see the different branches of the vascular system across the X. So arteries, for example, very high pressure, right? Between 75 and 100 millimeters of mercury. And we can see that it starts out high, but as soon as we get to the arterioles, it starts dropping off. And this is because the lumen of the arterioles, which is going to equate to resistance, the lumen here is smaller, which means we have more resistance, which automatically decreases our flow. As we get to the capillaries, similar scenario, even more resistance is encountered. Blood has slowed down significantly, and so we also have a drop off in the gradient. And so that kind of, slows down the flow. And then if you go all the way down to the CVP, the pressure in our veins, that's even lower. And if you think about it, that is important. We need to have this pressure be much lower than this pressure in order for blood to move. If the pressure in the veins was way up here, blood would not move throughout the circuit at all. Now, comparing that to the pulmonary side of the circulation, pulmonary pressures are much lower overall, but we still have a gradient, right? Important to understand. So lower pressures to start in the pulmonary artery, about, lower than 25 or so. And then that drops off as we get to the pulmonary capillaries. And then getting back to the pulmonary veins that come back to the atria, that is even lower, but there still is a gradient in order to move that blood through the pulmonary circuit. Now, as I mentioned earlier, the pressure gradient in the systemic circuit is greater than that in the pulmonary circuit. However, the pulmonary circuit has less resistance than we see in the systemic circuit. So overall, they both balance out, and the flow rate, right, the flow encountered through both of those circuits wind up being the exact same. All right, so let me say that again. Systemic circuit has greater pressure gradient, but greater resistance. Pulmonary circuit has a smaller pressure gradient, but also a smaller resistance. So the flow at both of these circuits ends up being the same, or ends up being equal. Let's talk about resistance. And resistance is the flow that is, or the force rather, that is opposing the direction of flow. And there are several other factors that affect the resistance to flow. And we're going to call that Q. Q is going to be the symbol that represents our resistance to flow. So the factors that affect that are the radius of the vessel, which is R. And in arterioles and small arteries, we can regulate the radius, especially by way of the autonomic nervous system and the smooth muscle found in those arterioles. So we can change and regulate the radius of those vessels. The length of the vessel, L, and that is how far blood has to travel. What is the length of that vessel? And then the viscosity of the fluid, in our case, blood, which is represented by the symbol here, it looks like an N. This is viscosity, and that tells us, what are the amount of particles dissolved in that fluid that will slow the fluid down? What is the viscosity? What is the thickness of that fluid? In our case, blood, and that will be determined by the amount of erythrocytes or RBCs and the amount of proteins that are found in the blood, although those two things are usually constant in our physiology. Okay, but when we look at things like certain types of anemia, we can see the viscosity of blood increase, and that can actually slow down the rate of flow as it introduces more resistance. So in typical healthy homeostasis, we don't really think about viscosity of blood changing, but that can change in some pathologic states. So these three factors influence resistance, and resistance in turn influences flow, okay? The radius of the vessel, the length of the vessel, and the viscosity of the fluid in the vessel. All right, looking at another scenario that now introduces the concept of the resistance. So on side A, we have our high pressure. On the right side, we have lower pressure. So the gradient here is the same in both of these scenario A and B. The gradient here is 40 millimeters of mercury in terms of the differential. However, in scenario A, we have less resistance because we have a larger diameter. Remember, radius is one of the factors that influences resistance. So a larger radius means that we have less resistance in this scenario. Scenario A, less resistance, that gives us a flow rate of 20 milliliters per minute. Alternatively, scenario B has a smaller radius, which means that it has more resistance. And that is going to result in a lower rate of flow. So the resistance, again, is inversely proportional to the flow. When the resistance goes up, the radius goes down and flow goes down. When the resistance goes down, the radius goes up and flow goes up.